Section 4, we have polyatomic ions. Poly, of course, means many. Atomic here just means atoms. And ions means that the atoms have a charge. And so what we have are many atoms working together as if they are a single ion having a charge there. And the example here is the hydroxide ion. There are all sorts of others, but we're going to get into those things here. So again, group of atoms that together have a charge. They usually are a non-metal, covalently bonded to oxygen. There are exceptions to that, and they usually have a charge of 1, 2, or 3 negative. Your major exception that's super common is the ammonium ion. It's NH4 with a plus charge, and these are things that, again, you need to have them on your note card, or you just flat out have to memorize the list of polyatomic ions, which is coming up here in a moment. I will point out that there's ammonia, the cleaner, and the gas. Usually that is ammonia dissolved into water, which forms the ammonium ion, but it is slightly different. Their names come from the same place, though. Here are some examples of polyatomic ions. In fact, there's the ammonium that we were just talking about there, but I'm going to move right along. Here is the list of polyatomic ions. They have them here broken down by what element is in them, and have them roughly in order of the number of oxygens bonded to them, counting down, and then counting down with the charges as well, it looks like. There are others. There are all sorts of others. And unfortunately, there are lots of similarities between them, and so it's very easy to get them confused. I'll be honest, when I was a student, I was told to memorize them. I didn't. We were given a quiz, and I did not do so well on that quiz, and I managed to stumble through the rest of chem not really knowing what I was doing. Until we got to acids and bases, all of a sudden when we got to acids, we had a list of acids to memorize. Those list of acids just clicked for me for some reason in a way that the polyatomic ions didn't, and then I could work backwards from there because I knew that acids had a hydrogen had a 1 plus charge, and since the whole thing had to be neutral, then say nitric acid, which has HNO3, well then that NO3 part had to be a 1 minus charge, and you'll see nitrate right there. And so I learned them a really backwards way, but it is much easier if you just memorize them. Again, you're allowed a note card with me on test. You can have them there. If you're live with me, there is a pattern, and I'll show you the pattern, and I would encourage you to use the pattern instead. It's a little bit hard to teach without a little bit more interactivity and me really being able to interact with the periodic table, but I'll maybe post a supplemental video if you're curious to see that. Either method works for learning your polyatomic ions. Even so, there are still exceptions, and nitrate actually happens to be one of those. Anyway, I'll point out that there's things like nitrate and nitrite, and so you have to be very careful when writing, when pronouncing these, that you say them carefully, write them carefully, because that difference is only one letter, and yet it's a whole oxygen that they are different by. I will point out that when you look at chlorine's polyatomic ions, they all have the same charge here, and they differ only in the number of oxygens. There is actually a rule that 8s are usually speaking, the most common one. Per 8s have 1 more oxygen, ites have 1 fewer oxygens, hypoites have 2 fewer oxygens, and the charges are different if we don't have just the element and an oxygen in there. As you'll see here with carbon, there's carbonate there, and then we have hydrogen carbonate, also known as bicarbonate, so we also have these that go by 2 different names. Cyanide, you might have heard that before, it's an incredibly toxic thing. Acetate, also known as ethanoate. And here's where we start to get into things that are organic in nature, and will come up more in Chem 111, and it's part of why it goes by more than one name as well, as there's kind of the organic way and the inorganic way of naming that one. In fact, there's a couple different ways I've seen this formula written even. So anyway, there's your list of polyatomic ions. You have it here in your notes, you have it in your textbook, you need to know it. As I said, the common ones end in 8. The ites have 1 fewer O. There are exceptions, which are these 2 major ones here, and then sometimes there's a hydrogen in there, and when we add a hydrogen, it's called bi, whatever the polyatomic ion name was, or hydrogen, and whatever the polyatomic ion name was. And so either one of those works. And then it mentions here that the halogens all form 4. They're not the only ones that form 4, but you can see the per 8s, the ites, and the hypoites here. When it comes to writing a formula with the polyatomic ions in there, you do the same thing. You just treat the polyatomic ion as one thing. I always like to write it inside the parentheses myself. Technically speaking, there's cases where the parentheses aren't necessary. I would say they're always acceptable. But they're only necessary when you actually have a number outside of them. I'll work out a couple examples on the next slide, but I want to show how to do the crisscross thing with this one rather than doing it the way that they do. Certainly that way works, but we have magnesium nitrate here, so magnesium has a 2+ charge. Nitrate, when you look it up on your list of polyatomic ions, you'll find out it's an NO3 with a 1- charge. We do the crisscross thing, we bring this 2 down outside there, we bring the invisible 1 down over here, and we end up with Mg, invisible 1, parentheses, NO3, close parentheses 2. If there is a subscript outside the parentheses are required and it stays. The one they want us to do here as an example, aluminum bicarbonate. So aluminum has a 3+ charge. Bicarbonate, you look that up on your list of polyatomic ions, you'll find out that it's an HCO3 and it has a 1- charge. And so we do the crisscross thing and we end up with Al, parentheses, HCO3, close parentheses 3. Sodium hydroxide. Well, sodium is an Na, and hydroxide is an OH. The hydroxide has a 1- charge, the sodium has a 1+ charge, so you do the crisscross thing and you end up with Na, invisible 1, OH inside parentheses, invisible 1. Well, when there's no subscript out here, it is acceptable to drop the parentheses. Another example, barium sulfate. Well, barium is Ba with a 2+ charge, sulfate, SO4 with a 2- charge. Do the crisscross thing. Oh, I didn't put that one inside parentheses. Do the crisscross thing, you end up with Ba2, SO4, parentheses 2. And this one, it turns out, can simplify. We never, and let me emphasize, never, to be very clear, never change the formula of a polyatomic ion. It always stays the same. That just is what the ion is. Bicarbonate ion is an HCO3 with a 1- charge. Sulfate is an SO4 with a 2- charge. Hydroxide is an OH with a - charge. We cannot change the polyatomic ion. In fact, I tell my students a lot of times to think of it as like sulfate is X, and I have Ba2X2 here. Well, if I had that, I'd know I could simplify it down. So I can do the same thing here. I can simplify it down to Ba, parentheses, SO4. And so this is one just showing you how the reducing and simplifying process works. However, now we have an invisible 1 outside the parentheses are no longer required, and BaSO4 is the correct way to write it. As I said, I've seen plenty written like this, and I think of it as acceptable to have the parentheses there when they're not necessary, but they are only necessary when you have a subscript outside of them, like there, or had this actually been a 2 subscript that stayed outside of the sulfate there. Another practice one here, sodium phosphate, Na. The phosphate is PO4. Sodium has a 1+ charge. Phosphate has a 3- charge. Do the crisscross thing, we end up with Na3, parentheses, PO4, close parentheses. And again, this is one where you could get away without writing the parentheses. When it comes to naming them, you really just have to identify the polyatomic ion. The nice thing is polyatomic ions are almost always anions. And because they're almost always anions, then they're usually going to be the last thing in there. Also, most ionic compounds are 2 elements bonded together. Well, if that one is your polyatomic ion, then there might be other elements here attached to this one, most commonly an oxygen. Your one exception is the ammonium, which is your positively charged one, so keep an eye out for that one. But the way I always say it is if you start checking your list of polyatomic ions and you can't find the thing you're looking for, and double check, make sure you don't have the one positive one in there. But when you look at this, you can see, okay, oxygen is going to tend to be part of the polyatomic ion. I want everything except for that metal. Everything except for the metal, and this one here, the parentheses are already here. It makes life simple. And then from there, we just name each piece. So that's still sodium, and SO4 is sulfate, which is different than sulfide. And so sodium sulfide would have been Na with a positive charge. Sulfide is S with a 2- charge. Do the crisscross, and we had 2s. I think that even came up as an example earlier. But the 8 means it's a polyatomic ion. The ide means it's a not polyatomic, it's a monatomic ion, if we want to be picky with how we name it. I think it's an unnecessary vocabulary word, but there you have it. Same thing comes into play with the transition metals. You still have to figure out their charges, and so the way that you figure out that one's iron 3 is the same as before. You just have to consider the whole polyatomic ions charge. 3 minus, there's one of them, so that gives me a total negative charge of 3 minus. I know the total charge has to be 0, and so then the positive charge must be a 3 plus, and since there's only one iron, then that one iron has to be a 3 plus, so iron 3 phosphate. That there is as complicated as ionic names get, is having a transition metal, so it needs a Roman numeral and a polyatomic ion. Here, like I said, the parentheses are there already, so they tell you the polyatomic ion, so that one's carbonate, and so then just aluminum carbonate. Here's a list of some other compounds as well as some of their uses. I would encourage you to take a moment, pause it, read through it. I will also say that if you want to get familiar with chemical names, start reading your ingredients labels, especially on hygiene and medical products. You'll find these names are all over the place, and they actually help you get kind of used to it and get to where you're comfortable handling them. This one here is set up as a multiple choice. I'm going to work it out the crisscross way, the way that I've been doing. So aluminum has a 3 plus charge. Nitrate is an NO3, and it has a 1 minus charge. So we do the crisscross thing, and we end up with Al invisible 1. NO3 close parentheses 3, and so that one's going to be this one here. Copper 2 nitrate, so we've got the nitrate polyatomic ion there again, but Cu with the 2 plus charge. Nitrate, as we just had, is NO3 with the 1 minus charge. And so then crisscross Cu parentheses NO3 close parentheses 2, so that's this one here. Iron 3 hydroxide, Fe with the 3 plus charge, hydroxide OH with the 1 minus charge, do the crisscross thing, Fe parentheses OH close parentheses 3, and that's going to be this one. And then 10,4 hydroxide, that's going to be Sn with a 4 plus charge, hydroxide's OH with a 1 minus charge, and so we do the crisscross thing and we end up with the Sn parentheses OH close parentheses 4, which is this one down here. The reverse process of naming them is just as easy here. So we have calcium there, and then you look up NO3. We don't have to worry about the number 2 outside there, and that's nitrate. So calcium nitrate. This one here being 10, it's going to need a Roman numeral. So 10 Roman numeral sulfate. Going back and figuring out the Roman numeral there. Sulfate has a 2 minus, and so our total negative is 2 minus. Total positive has to be 2 plus. Since there's only one of them, then 10 must be a 2 plus, and so Roman numeral 2, 10,2 sulfate there. Over here, just some more practice naming. So first one is magnesium. Sulf. This time it's ite, I-T-E. And then we have magnesium sulf 8. This one here is about as hard as they get because we have a transition metal that's going to need a Roman numeral and a polyatomic ion, and it's actually one of the not 8s, which are the less common ones, so you'll be less familiar with them as time goes on. But lead, Roman numeral, phos, and then this is ite with an ITE suffix there. The 8 is an O4. And then we need to figure out the charge on here. So phosphite has a 3 minus charge. That gives us a total of 6 minus. We know the, for the negative, we know the total charge has to be 0. It has to be neutral. And so the positive charge must be a 6 plus to cancel that out. That 6 plus is split up or shared between 3 lead atoms. So then each of those lead atoms must be a 2 plus. So Roman numeral 2, lead 2 phosphite. Some more practice naming here, and so here we have iron, and then Roman numeral, sulf, and then O4 is 8, and so then we have a 2 minus, that gives us a total of 6 minus, which means we must have 6 plus. There's 2 of them, so that's 3 plus. Iron 3, sulf 8. Here, barium is one of the ones that always has a fixed charge, so we don't need the Roman numeral thing. Barium, phos, there they gave us phyte again with the ITE suffix, and then this one here is nickel And then we'll need a Roman numeral, carbonate. I'll point out this is one where the dropping the first syllable doesn't apply. In fact, for whatever reason, on carbon we call it carbide when it's a single ion, but we call it carbonate, and we don't actually drop any of it instead of calling it carbate like it probably should be. Anyway, just have the list, know the list, refer to the list. You don't need to worry about any fixed set of rules for where their names come from. So for the Roman numeral, carbonate has a 2 minus charge. There's one carbonate there, so that gives us total 2 minus. So then nickel must be a 2 plus. There's only one of them this time. And so then that one nickel gets all of that 2 plus, and it's nickel 2 carbonate. And that finishes up section 4.